Transition elements are elements that lie in the middle of the periodic table. With this position in the periodic table, it seems clear that these elements have partially filled the orbital. Based on the location of transition elements, we expect them to have properties that lie between the metallic S block elements and the P block nonmetals. First, let's look at the atomic radius of transition metals. Generally, the atomic radius decreases gradually from left to right due to the added nuclear charge. Remember, from left to right, there are added nuclear charges that cause a decrease in the atomic radius due to the attraction between the nuclear charge and the negative electrons. But there are added negative electrons as well to the same energy level that causes an increase in the atomic radius later on. At first, the attraction due to the increase of nuclear charge overcomes the repulsion between electrons, leading to a decrease in the atomic radius. Somewhere in the middle, the repulsion between the added electrons overcomes the effect of the increase in the nuclear charge and causing an increase of the atomic radius. Let's move to density. Density increases steadily due to the increase in the atomic radius. But once again, around the middle, the atomic radius starts to increase, which causes a decrease in the density. For similar reasons, the first ionization energy increases across the transition elements as the nuclear charge increases. Transition elements have high melting and boiling points. Metallic bond forms between atomic valence electrons. As the number of the valence electrons increases, the strength of the metallic bond increases as well, resulting in an increase in the melting and boiling points. There is a large number of bonding electrons comparing to metals in S-block elements, which makes the melting and boiling points of transition elements higher than S-block metals. Although transition elements and S-block elements both are metals, there are some discrepancies between them. Let's compare calcium in the fourth period with transition metals in this period. Melting points of calcium is lower than of transition metals. Density is lower as well. The atomic radius of calcium is larger and the ionic radius as well. First ionization energy is lower and the electric conductivity of calcium is higher than transition metals in that period, except for copper. Now, you need to remember across the period, the nuclear charge, valence electrons, and the number of bonding electrons all are increasing. This means the atomic and ionic radius decreases across the period. This decrease causes an increase in the melting and boiling points, and for similar reasons, the first ionization increases across the period. As for density, the mass of transition metals is higher than calcium because they have larger atomic masses. Now moving to redox reactions for transition metals. Redox reactions are any reactions where elements have different oxidation states. Transition elements have different oxidation states, and they have the ability to get involved in reactions where they change their oxidation states. What characterizes transition elements? They have different colors for the different oxidation states. For example, the pale yellow iron 3 ions are reduced to pale green iron 2 ions. You can see that iron can act as an oxidizing agent by acquiring one electron from the other half equation, and that the standard electrode potential is equal to 0.77 volts. Another example, manganese 7 oxide acts as an oxidizing agent, taking away 5 electrons from the other half reaction to be reduced to manganese 2 ions. You can see from the previous example that permanganate 7 oxides can oxidize iron 2 ions to iron 3 ions. The standard electrode potential is equal to 1.52 volts, which is higher than the iron half equation. Let's combine the two equations. When we combine the two half equations, we need to multiply the iron half equation by 5 because permanganate needs 5 electrons to be reduced. You can see that we reversed the iron half equation and give the iron half equation electrode potential a negative value. The reason behind that is the standard electrode potential of permanganate is higher than the iron-half equation. That is why it acts as a strong oxidizing agent and oxidized iron 2 ion into iron 3 ion.